The chemistry of 3D elements is very interesting and quite different to those of S and P block elements. This video supplements the level 4 inorganic chemistry course CHU 2123 and inorganic practicals conducted at level 3. We intend to look at the following aspects of 3D elements: electron configurations of 3D elements, properties of 3D elements, test for common cations, and uses of 3D elements. Let us start by looking at the periodic table. The periodic table has 18 groups. These groups fall into S, P and D blocks. The elements in the groups 1 and 2 belong to the S block. Groups 13 to 18 belong to the P block. The elements in the groups 3 to 12 belong to the D block and it is situated between the S and P blocks. Lanthanides and actinides belong to the F block. Mainly, there are 3 horizontal rows in the D block. They are called 3D, 4D and 5D series. In this video, we concentrate only on 3D elements. They are scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. Each 3D element has 5 3D orbitals. They are dxy, dxz, dyz, dx squared minus y squared and dz squared. Each orbital can occupy a maximum of 2 electrons. These d orbitals are divided into 2 groups, T2g and Eg. In an isolated atom or ion, all 5d orbitals have the same energy. But in a complex, these orbitals split into 2 different energy levels depending on the geometry. The filling of 3D orbitals results in 3D elements. Electron configurations of 3D elements. Let us look at the electron configurations of the 3D elements. Scandium has 2 4s and 1 3d electrons in addition to the electron configuration of argon. The group number is equal to the sum of S and D electrons. Look at the electron configurations of chromium and copper. There is only 1 electron in the 4s orbital. Properties of 3D elements. All 3D elements are metals. Each consists of a lattice of positively charged ions and a pool of free electrons. Thus, they are good thermal conductors. And they are good electrical conductors too. When compared to S block elements, 3D elements have higher melting and boiling points. Zinc has the lowest melting point, whilst vanadium has the highest melting point. They have relatively higher densities when compared to S block elements. 3D elements are less electropositive than S block elements. Unlike scandium and zinc, other 3D elements show variable oxidation states. The most stable oxidation numbers are highlighted. 3D elements or their compounds can act as catalysts. For example, titanium chloride is a catalyst for polymerization of olefins. Vanadium pentoxide for manufacture of sulfuric acid. Manganese dioxide catalyzes the decomposition of hydrogen peroxide and potassium chlorate. Iron and iron oxide are used in the synthesis of ammonia. Ferric bromide catalyzes bromination of benzene. Ferrous ions catalyze the oxidation of iodide by persulfate. Nickel is used to hydrogenate olefins. Cuprous chloride for the preparation of chlorobenzene from the diazonium salt. Unlike scandium and zinc, other 3D elements form colored compounds. Why these are colored? The energy difference between these two levels is related to the frequency nu as delta E equals to the h nu. The frequency of a photon carrying these energy quanta lies within the visible region of the spectrum. That is why most of the d block complexes are colored. White light consists of all the frequencies in the visible region. When white light falls on a complex, an electron in the ground state is excited to the higher energy level, absorbing a certain color. In this case, it is the red color. Then, what we see is a combination of the remaining colors, which is known as the complementary color. Using a color wheel, we can find out the complementary color. In the color wheel, the complementary color is shown opposite to the color absorbed or vice versa. Test for common cations of the 3D elements. Test for chromium 3+ ions. To a solution of chromium 3+ ions, add a small amount of ammonium hydroxide solution. A green precipitate of chromium hydroxide is formed. Take another solution of chromium 3+ ions. And add sodium hydroxide. Followed by hydrogen peroxide. Yellow solution of sodium chromate is formed. Then add barium chloride solution. A yellow precipitate of barium chromate is formed. Addition of dilute nitric acid to this precipitate gives a violet solution. Test for manganese 2+ ions. Sodium hydroxide is added to a solution of manganese 2+ ions. A white manganese hydroxide precipitate is formed. It slowly turns black when exposed to air. Addition of ammonium sulfide to a solution of manganese ions gives a pink precipitate of manganese sulfide. Test for ferrous ions. Add a solution of ammonia to a solution of ferrous ions. Ferrous hydroxide precipitates as a green solid. Addition of ammonium sulfide to a solution of ferrous ions gives a black precipitate of ferrous sulfide. Take a solution of ferrous ions, add a solution of potassium ferricyanide. A Prussian blue precipitate is formed. Test for ferric ions. To a solution of ferric ions, add a solution of ammonia. A brown precipitate of ferric hydroxide is formed. A solution of ammonium thiocyanate is added to a solution of ferric ions. A red solution of ferric thiocyanate is formed. To a solution of ferric ions, add a solution of potassium ferrocyanide. A Prussian blue precipitate is formed. Test for cobalt 2 plus ions. To a solution of cobalt 2 plus, add a solution of ammonium sulfide. A black precipitate is formed. Test for nickel 2 plus ions. Ammonium hydroxide is added to a solution of nickel 2 plus ions. A green precipitate is formed, which dissolves in excess of ammonia to give a blue solution. To a solution of nickel 2 plus ions, add a solution of ammonium sulfide. Black nickel sulfide precipitates. Take another solution of nickel 2 plus ions. Add a solution of ammonia and a solution of dimethyl glyoxine. A red precipitate of nickel complex is formed. Test for cupric ions. Add a solution of ammonium sulfide to a solution of copper 2 plus ions. Black copper sulfide precipitates. Sodium hydroxide is added to a solution of cupric ions. Pale blue cupric hydroxide precipitates. Which on boiling turns black. To another solution of copper 2 plus ions, add an excess of ammonia. A deep blue solution is formed. Test for zinc 2 plus ions. To a solution of zinc ions, add a solution of ammonia. White zinc hydroxide precipitates, which dissolves in an excess of ammonia. addition of ammonium sulfide to a solution of zinc ions gives a white precipitate. Some uses of 3D elements. Scandium. Scandium is used in electronic devices and high-intensity lamps. Apparently, scandium is a component of alloys used to make metallic baseball bats. Titanium. Titanium and its alloys are used in aircraft industry. Titanium has excellent resistance to seawater and is used to produce parts of ships. Titanium dioxide is used as a white pigment in paints. Vanadium. Vanadium is used for producing rust-resistant springs, steels and tools. It is used as ferrovanadium. Vanadium pentoxide is a catalyst for the oxidation of sulfur dioxide to sulfur trioxide. Chromium. Chromium is used to harden steel. It is used as a protective coating. Chromium oxide is a green pigment. Manganese. Manganese forms many alloys with other metals. Manganese dioxide is used in black paints and it is a depolarizer in dry cells. Manganese dioxide is also used to decolorize glass. Iron. Iron is used to produce other alloys including steel. Iron or its oxide is used as a catalyst in Haber process. Cobalt. Cobalt-60 is a gamma ray source. It is used to produce magnet and stainless steel. Blue color in porcelain, glass and pots is mainly due to the cobalt salts. Nickel. Nickel is used as a catalyst in the manufacture of margarine. Nickel 2+ ions are found in enzymes such as hydrogenase and urease. Copper. Copper is a good electrical conductor and a coinage metal. Copper sulfate is used as an agricultural poison. Zinc. A large proportion of all zinc is used to galvanize metals. Zinc sulfide is used in making luminous dials and TV screens. Zinc oxide is used in the manufacture of paints, rubber products and cosmetics. In conclusion, we have discussed the important aspects of 3D elements, particularly their properties, tests for cations and their applications. We hope you have gained additional knowledge in 3D elements.